All right, there are a lot of radial Navier-Stokes radial Navier-Stokes problems that we could do. I picked the more mind-bending one, I guess, the one that's more different than traditional ones. So, because if you can understand this, you can probably understand anything. So, radial Navier-Stokes, we now deal with cylinders instead of channels. Or tubes instead of channels. So for this specific problem, there's an inner cylinder, which that one is, and there's an outer cylinder, which is right here. The inner cylinder is rotating at a angular velocity omega, and it's like, what the heck do you even do with this, bro? Like, what? But I'm pulling up my equation sheet. So you can do a couple of things with this. First, let's write a couple dimensions and that sort of stuff. So the inner cylinder, I'm going to draw a dotted line as a center line. The inner cylinder has a rate, oh, that's too big. R1, outer cylinder, that's too big. Sure. R2. Okay, pretty straightforward so far. Now let's get into the coordinates. So before we had x, y, and z was like out of the page. Not anymore. Not anymore. Well, okay, I'm going to keep that up here for a second. X, y, z, and this was u, v, w. Now, I'm going to draw it along the center line because it'll make the boundary conditions nice. We have, what do we have? We have z, oh, that's a v, z, which is w. We have r, I'm going to draw this line a little longer actually. R, which is u. And we have this, which I'll explain in a second, which is the theta direction, and it is called V. And it's kind of hard to visualize it with the way I drew it. What do they do? I think X is into the page and a dot is out of the page. So that's a dot. That's pointing out. And the way you can do it is if you put your thumb in the Z direction, your fingers curl around such that if you look at it from, let's say this is your head, that's your eyeball, you're looking that way, it would be rotating counterclockwise. Yeah. Okay. Dang, in high school or even at the beginning of college, I never would have, or even in the middle of college, I never would have stressed out about these freaking dimensions, but they actually matter. Dang, I feel old now. All right, boundary conditions. Right there, we have, which one would it be? It would be theta, wouldn't it? Yeah, it would. So if the theta, so since it's rotating, it would be V, so the theta direction, the omega direction, because omega is the same direction as theta. So V at R, well, at R equals R1 equals, the velocity would be omega R1. Yeah. Out here, V at R equals R2 equals 0. No slip, the outer cylinder is stationary. There's also the no penetration, but let's skip that for now, and if we need to, we can write it later. Those are the two big ones. Okay. Let's, what do we do? All right, let's write out the Navier-Stokes equations. Well, oh, we got to do assumptions. Always do assumptions. There are a couple weird ones. So it was stated that W, so the velocity in the z direction, is 0. It was stated in the problem statement. Yeah, it was stated in the problem statement that equals 0, which makes sense in this problem because it shouldn't be going that way. It should just be rotating. So that was stated. It was also stated that dp dz equals 0. And we assume that it's axisymmetric. And that means, it's weird. It means that it's basically like an infinitely long in x, but it's axisymmetric in theta. And it means du d theta equals dv d theta equals dw d theta equals dp d theta equals 0. And normally, like not axisymmetric, in fully developed, where it's all the dx's are 0, the dp dx isn't included in that. But here, for axisymmetric only, you include this. I still don't really understand. My teacher explained it to me once, but like I don't really understand. I just wrote it down. But yeah. So these are our assumptions. So, all right, the Navier-Stokes equations are wild. But let's do them. So there's one in each direction. Let's do the one in z first. There you go. It's freaking ugly, and it is the least ugly of the three, which is wild to say. But in this case, there's almost no point in me doing it because w equals 0, and it was stated. So w equals 0, so all the derivatives of it are 0. So all of it cancels out and it goes away. Same thing. Maybe not same thing in the R. You know what? I don't even want to try it right now. Let's go in the theta direction because that's what we care about in this problem. I don't want to freaking waste any more time writing this stuff out. This is a V. I forgot to do the continuity equation. We'll do that in a second. You have to sit through me writing this stuff out so you know never to give your future students any of these problems. Yeah, that's probably right. All right, I'm gonna pause here and I'm gonna write the continuity over here. So what is the continuity? It is du dr plus u over r plus 1 over r dv d theta plus dw dz equals 0. Yep. I don't know either. All right, with respect to theta goes away. Axisymmetric. W equals 0. So we're left with these two terms. U dr plus u over r equals 0. Okay. Yeah. Let's group them. 1 over u du equals 1 over r dr. Now integrate both sides, and we'll get ln of u equals ln r plus a, constant. And then let's put both of them to the e to get them out of the natural logs. Plus a. And then the left side cancels out, so we just have u. On the right side, we have e ln r. This can go to this. Yeah, because if you have a plus in here, you can break them apart. And then that equals r e to the a, and we'll assume e to the a, well, okay, let's assume a equals like 10. Then e to the 10 is another number. I don't know what it is, but it's a number. Let's say it's 105. I don't know, but it's another number. It's another constant, so we can also call it a, because we don't even know what a is, so we can just do that. Oh, I forgot something. There's a negative here. Okay. A over R. Yep. All right. Dang, that's a long line. It's a long line. Look at that. What do we know about U? Which direction was U? U was a radial direction, and no penetration at either of these 2 points. So U R equals R2 equals 0, because it can't go through the wall and it can't come out of the wall because it's a wall. And same down here, U R equals R1 equals 0. We only have one unknown, just A, so we can whichever one of those we want. BC, UR equals R1 equals 0, which equals A over R1. So A has to equal 0. Cool. That means that U equals 0. And U is the R direction. So if we drew out the R direction, Navier Stokes, we'll get all of the terms on the left side and all the terms on the right side canceling out. We'll be left with dp dz, and then we'll integrate it once, and I don't know, there will be a constant in there, but it doesn't matter. All right, back to the theta direction. So dv dt, did I assume steady? I better have assumed steady. Yeah, I did. Steady d dt equals 0. Steady state. What did we say? We said U is 0. U is 0. U equals 0. U equals 0. 2D axisymmetric fully developed. Why did I cancel it out? That's the wrong reason. It should be fully developed in Z. I'm gonna write it here. Fully developed. Because it's an infinitely long tube. That is a terrible drawing. Infinitely, this is still a terrible drawing, but whatever's going on here, same as what's going on there, same as what's going on there. So there's no slope between those 2 points. Okay. So we have all the terms cancel out except for this term. So just like the normal Navier Stokes, a lot of stuff canceled out here too. So we have 0 equals that d dr 1 over r d dr rv. Is that what I have? Better be what I have. Yeah, probably. Okay, so we can cancel that out because we just divide it to the other side, but 0 over that is still 0. We have d dr 1 over r dr rv equals 0. So then integrate both sides, end up with 1 over r d dr rv equals a constant, I'll call it a. Multiply both sides by r, so then we have d dr rv equals ar. Integrate again, rv equals 1/2 a r squared. V equals up plus b. Yeah. V is 1/2 AR, because you divide by R, plus B over R. And that is wild, isn't it? Okay. Now we have our two boundary conditions. We have that V at R1 equals omega R1. V at R2 equals 0. So let's do that one first. So then, what do we want to do? Solve for A. Negative B over R2 times 2 divided by R2, so R2 squared, right? It's probably right. V at R equals R1 is this times R1, which equals, we solved for A, didn't we? Oh, so the 2 cancels with that. So we have negative B R2 squared R1 plus B over R2. That's probably right. And then you can solve for B. And that should be doing a lot of math in my head here, which you should not do. You know what? I'm not going to do a lot of math in my head. Yeah, okay. Might have made a small algebra mistake. I don't know. I don't really care. But that's B, and then you plug it in up here. It's a bad line. Plug it in up here, and you solve for A. But yeah, that's literally it. This is the final form. You plug in A and B. Plug in A, plug in B. That's it. I plotted it just to make sure it seemed reasonable, and it did seem reasonable-ish. Let's say the freaking cross-section, if you look at it from the side, like this is rotating like that, it looked, I don't know, it was like, profile was like that or something. So it went in the right direction. This was not a line. It was like I don't know, it was a weird curve or something, but it went in the right direction and it looked fine, so I'm guessing it's fine. Yeah, freaking radial coordinates. Sucks, but it's really not that hard. It's like normal Navier Stokes. But yeah, that's about it.